You clicked because you saw claims about running massive AI models on consumer hardware. You want to know if you can actually generate text at 80 tokens per second with 128,000 tokens of context on a 12 GB graphics card. The stakes are high because your current setup feels limited, and you are tired of relying on slow cloud APIs or expensive enterprise hardware to get good results. By the end of this video, you will understand exactly why that specific promise holds true for some engines, but fails catastrophically for others, and you will know the architectural reason behind the difference. There is a prevailing narrative in the developer community that multi-token prediction has broken the physical laws of hardware requirements. The story goes that by predicting multiple tokens at once, we can bypass the speed limits of consumer GPUs and handle massive context windows without breaking a sweat. This sounds like the perfect solution for any junior engineer looking to build production-grade applications on a budget. It suggests that the era of being locked out by hardware costs is over. But when we look at the actual performance of the qwen 3.635 billion model with its 3 billion active parameters, the reality is far more complex and nuanced than the marketing suggests. To understand the discrepancy, we first need to look at what multi-token prediction actually does. This technique allows the model to generate several tokens in a single forward pass instead of just one. In theory, this should linearly increase throughput. If you can predict 3 tokens per pass, you should theoretically triple your speed. The logic is sound on paper. However, the physical world of computer architecture introduces friction that theoretical models often ignore. The qwen model uses a mixture of experts architecture. This means that for every token generated, the system must route the computation to specific subnetworks or experts within the model. This routing process itself consumes bandwidth and adds overhead that becomes a bottleneck when you push the system to its limits. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Now consider the hardware you are likely using, such as the RTX 3090. This card has 12 GB of video memory and relies on an Ampere architecture. The Ampere architecture has specific bandwidth characteristics that interact poorly with the demands of multi-token prediction when combined with mixture of experts routing. The bandwidth saturation occurs because the system needs to fetch data from different experts simultaneously. When you try to run this on a consumer card, the data movement required to coordinate these experts overwhelms the memory bus. The result is that the theoretical speedup is completely negated by the time spent waiting for data to move around the chip. This brings us to the specific performance numbers that define the current state of the art. When we run the qwen model using the vLLM inference engine, we do see a tangible benefit. The system achieves a 27.5% speedup compared to standard generation. This is a real gain, and it is enough to make the model feel snappier in a production environment. However, when we switch to llama.cpp, which is a popular choice for local deployment, the results are the opposite. Implementations of speculative decoding with multi-token prediction in llama.cpp suffer from a 40 to 52% performance degradation. Instead of getting faster, the generation becomes significantly slower than the baseline. This regression is not a bug in the model, but a fundamental incompatibility between the inference engine, the model topology, and the memory bandwidth of the consumer GPU. You might be wondering how this relates to the claim about handling 128,000 tokens of context. This is where the memory constraints become the primary bottleneck. Even if we could solve the speed issue, the memory requirements for a model of this size with such a large context window are simply too high for a 12 GB card. To maintain a comparable 35 billion class model with 128,000 tokens of context, you need approximately 17.9 GB of video memory. This exceeds the physical capacity of your graphics card by nearly 6 GB. Consequently, the system is forced to offload a significant portion of the computation and memory storage to the central processing unit. This offloading strategy introduces a massive latency penalty. The central processing unit is orders of magnitude slower than the graphics processing unit when it comes to matrix operations. As the system constantly swaps data between the fast video memory and the slower system RAM, the generation speed grinds to a halt. The promise of massive context on consumer hardware currently relies on aggressive quantization techniques to squeeze the model into the available memory. But even then, the speed is compromised. You are trading raw throughput for the ability to fit the context window into the available space. The multi-token prediction technique does not eliminate this physical memory ceiling. It cannot create more video memory out of thin air. So what is the takeaway for someone building production systems? The belief that multi-token prediction universally breaks hardware constraints is qualified by specific architectural details. While the technique does accelerate inference in the right environment, it does not solve the fundamental physics of memory bandwidth or the capacity limits of consumer hardware. Practitioners must recognize that achieving high performance with large context windows requires a careful balance of inference engine selection, model topology, and quantization strategies. You cannot simply apply a speedup technique and expect it to work across all hardware configurations. The interaction between MOE expert routing and memory bandwidth is the critical factor that determines success or failure. If you are planning to deploy these models, you need to test your specific stack before committing to a production workflow. Do not assume that a technique that works for one model or one inference engine will work for another. The landscape is shifting rapidly, and what works today might be obsolete tomorrow as new architectures emerge. The key is to understand the underlying mechanisms rather than relying on headlines. By recognizing the limits of your hardware and the specific requirements of the model, you can make informed decisions that lead to reliable and efficient systems. This knowledge empowers you to build better applications without being held back by unrealistic expectations. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.